Hey everyone, and welcome back to Everything Explained in 5 Minutes. Today, we're charting new frontiers, literally, in space exploration. For the first time ever, astronomers have produced a three-dimensional map of an exoplanet's atmosphere, revealing weather patterns on a world outside our solar system. Let's unpack how they did it, what they found, and why it matters. What's the breakthrough? Earlier this month, the European Southern Observatory's Very Large Telescope in Chile probed the atmosphere of WSB 121b, a hot Jupiter some 850 light-years away. Using a technique called high-dispersion spectroscopy, they measured how starlight filters through different layers of the planet's atmosphere during transit when the planet passes in front of its star. By examining shifts in the wavelengths of specific elements, scientists reconstructed a 3D model showing temperature, wind speed, and chemical distribution at various altitudes. en.wikipedia.org. How does high-dispersion spectroscopy work? Imagine looking at a rainbow, but instead of colors, you see tiny spectral lines, each corresponding to a chemical fingerprint, like iron or titanium. At very high spectral resolution, the telescope detects minute Doppler shifts in those lines as gas moves toward or away from us. When WSB 121b orbits its star, different atmospheric layers rotate and flow at different speeds. By timing these shifts across the transit, astronomers separated signals from the planet's near side, far side, and limb, building up a three-dimensional picture. Key findings on WSB 121b. Iron and titanium vapors stream around the planet at thousands of kilometers per hour. Dayside temperatures exceed 2,500 degrees Celsius, hot enough to vaporize rock. Thermal inversion layers appear, where upper atmosphere is hotter than layers below, likely driven by strong stellar irradiation. Eastward equatorial jet streams transport heat from the blazing dayside around to the cooler night side. This is the first time we've seen weather on another world, winds, temperature gradients, and chemical layering in 3D. Why it matters? Climate and circulation models. Just as we model Earth's atmosphere to predict weather, this pushes exoplanet climate science into 3 dimensions. We'll be able to test theories on atmospheric dynamics under extreme conditions. Chemical signatures of habitability. Mapping where molecules like water or methane reside could tell us which planets might support life, or at least have temperate zones. Benchmark for future telescopes. The James Webb Space Telescope and the upcoming ELT, Extremely Large Telescope, will build on this, probing smaller, cooler planets with the same 3D techniques. Understanding planetary evolution. Hot Jupiters like WSB 121b are extreme cases, but by studying them, we learn how atmospheres respond to intense radiation, shedding light on atmospheric escape and long-term planet survival. What's next? Astronomers are already planning similar observations of other exoplanets, both hot Jupiters and warm Neptunes, to see how atmospheric dynamics vary with mass, composition, and stellar type. The goal: a catalog of 3D atmospheres, turning exoplanet science from one-dimensional snapshots into full weather maps. In 5 minutes, we've gone from a point of light in the sky to a dynamic, swirling, three-dimensional world, mapping winds, clouds, and chemistry on a planet orbiting another star. It's a leap that transforms exoplanet studies and brings us one step closer to understanding the diversity of worlds in our galaxy. That's the first 3D map of an exoplanet atmosphere, explained in 5 minutes. If this sparked your curiosity, hit follow and share it with your fellow stargazers. Until next time, stay curious and keep looking up.